With this lesson, we're going to be continuing our discussion of similar triangles, and we're actually going to use that to tie into the beginning of proper trigonometry, what most people think of as classical right-angled triangle trigonometry. So you can see here I actually am starting with a couple of right-angled triangles, and I'm going a little further than that. Not only are they right-angled triangles, but you can see I've marked the corners here with this purple X, and then the other corners with the other vertex with this red dot. So that implies that we have, obviously, right angles are equal to each other, and then the top right corners, the corresponding top right corners are equal, the corresponding bottom left corners are equal angles. So we are able to make this similarity statement. This is angle-angle similarity. So triangle ABC is similar to triangle JKL. And as we've looked at with similar triangles, that means that the ratios of corresponding sides are equal. So AB, which corresponds to JK, that ratio is equal to BC, which corresponds to KL, and AC, which corresponds to JL. And if you take a look, AB over JK, 5 over 10, that's a half. BC over KL is 3 over 6, that's a half. AC over JL, that's 4 over 8, that's a half. And of course, all of the angles are equal. We knew that already because that's how we showed that they were similar. Now, everything we're going to do from this point forward in today's lesson is going to be related to the fact that we've got right angles here. So don't lose sight of that as we're going forward. Okay, so with similar triangles, we were looking at different triangles and we were calculating the ratios between the triangles. So for example, I might look at the triangle ABC and compare that, come up with ratios compared to the similar triangle JKL, because these are similar. Notice I've got the right angles in each corner. I have the X's in the top right corner. I have the dots in the bottom left corner. So since all of the angles match in these triangles, all of these triangles are similar to each other. So with similar triangles, we look at ratios between triangles. So I might compare the sides of this triangle to the sides of this one, or the sides of this smallest one to the sides of this largest one. But I just want to ask the question now, well, what if I ask about the ratios within a triangle? So for example, I take BC divided by AC. And the way I chose these is, or the way we can figure out which ones I chose, you can see that the BC side, that's the side that runs between the 90-degree angle and the X. And the AC runs between the 90-degree angle and the red dot. So these triangles are all oriented the same way. So this vertical side you can see between 90 and the X is this side. So what if I do that same ratio? So the vertical side, the way they're oriented, 6 divided by 8. So the first one gave me 3 over 4, which is 0.75. The second one gives me 6 over 8, which of course is 3 over 4 as a reduced fraction, or 0.75. And then here, if I do a ratio of the vertical side over the horizontal side, QR over PR, 9 over 12, that reduces to 3 over 4, which is 0.75. So in these triangles, they're already similar to each other. But once I have similar triangles, which says something about their angles, now I end up with this interesting idea that the ratio between, in this case, the vertical side and the horizontal side is actually independent of the size of the actual sides. All that matters here is the ratio. So that is the beginnings of trigonometry. The idea that I don't actually care how big sides are. All I care about is the ratio between sides. That's what trigonometry concerns itself with, at least in the beginnings, the basic way. Okay, so let's take a look at this one. So if I have yz over xz, and that's equal to 0.75, remember we got that result before. So what does that tell us? Well, we've got this right triangle here, and we know that the ratio we know the ratio of this side to this side is the same as the ratio from this side to this side. So are these triangles similar though? Do we actually have enough information to know whether or not these triangles are similar? Well, we actually kind of do, just with this, because the side, if I cross multiply this, the side YZ is the same as 0.75 times the side XZ. So that means that if this is the side YZ, then this is 0.75 times YZ. And then if I were to take the ratios of this side to this side and this side to this side, it would turn out that I would actually find out that those ratios are equal. So it turns out that yes, these triangles are similar. I'm not going to do the entire demonstration of that. You can explore that if you want to. But more importantly, if they are similar, one of the things that similarity tells us is that corresponding angles must be equal. So even though I don't actually know the size of any one of these sides, just by virtue of the fact that we had this right angle here and the fact that we had this ratio present in both of the triangles, because of that, we're actually able to say quite a bit about the angles here. So let's go a little bit further with that. Right now I'm very much giving a kind of a loose demonstration and explanation of this. So once again, so just a reminder, similar triangles, we work between triangles, and with trigonometry we start to look at the ratios not between triangles, but we actually start to look at ratios within triangles. And so we've done this already about getting these angles of 0.75. So we are going to be focusing on right triangles, and in right triangles it turns out that the ratio of the sides is related to the angles in a very predictable way. And when I say angles, I mean these angles that I actually don't know yet. I don't need to say anything more about the right angle. It's a right angle. It's 90 degrees. So, for example, when I take a look at these two right triangles and I see that the ratios of their sides are equal, that tells me something about the angles as well. And that's what trigonometry is to start, which is the study of how side lengths relate to the angles. Okay, so let's take a look at some right-angled triangles and the idea of ratios, because that's what we're going to be using. Now, first of all, we must have a right-angled triangle. And then the next thing we do is we say, okay, what angle is it that I'm interested in? So we're not interested in the right angle because we know it. So we pick one of the other two angles. And depending on where we pick that other angle, and that other angle is known as the angle of interest, we label the other sides appropriately. Now the hypotenuse never gets changed. The hypotenuse is always across from the right angle. It is always opposite to the right angle. But depending on where I put this angle, and this is the Greek letter theta, that's a typical symbol. Sometimes you'll see X, but more often for angles we actually use Greek characters. So depending on where I put this angle of interest, I then label the side that is opposite to theta, and I label the side that is adjacent to theta. And remember, the first side you're going to label is the hypotenuse, so when you're choosing opposite and adjacent, you're only choosing between two sides. The hypotenuse is already well defined by the presence of that right angle. That's one of the reasons why these have to be right angle triangles. Okay, so when we have labeled our triangle correctly, we've got all the different components labeled, we've picked our angle of interest, then what we have are three primary trigonometric ratios, which essentially is saying there are three ratios that we form using these sides that we're going to be interested in. There are actually 6 in total, but the primary trigonometric ratios, there are 3 of them. One of them is, for this angle of interest, I'm going to be interested in the ratio of this length of this opposite side compared to the length of this hypotenuse. So I make a fraction, opposite divided by hypotenuse. There's another ratio called the cosine ratio, and so for this angle of interest, it's going to be the adjacent side, the length of the adjacent side, divided by the length of the hypotenuse. And then finally we have what's known as the tangent ratio, which is the opposite side divided by the adjacent side. So those are my 3 primary trigonometric ratios. To help you remember that, we have this thing called SOH CAH TOA. And SOH CAH TOA is known as a mnemonic. A mnemonic is just something you use to remember other things. And the way SOH CAH TOA works is we have the S is sine, and then this is sine equals opposite over hypotenuse. You can see I've got that down here. So sine equals opposite over hypotenuse. There's no theta here, but it's always sine of whatever the variable is you're using for your angle of interest. And then this one is cosine equals adjacent over hypotenuse. And the last one is tangent, which is equal to opposite over adjacent. And you can see SOH CAH TOA. You can also remember it this way if you like, or sometimes I've seen it written this way, SOH CAH TOA. Right? So this makes it even more clear that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. Whichever you prefer. To be honest with you, you don't even need to use this. You're going to hear it a lot in class, but if you're the kind of person who just remembers this, then just go ahead and remember it. That's fine. But it is something you are going to want to have in your memory. Okay, now, with a lot of math, and this is not an exception, the idea of studying triangles, studying triangle sides goes all the way back to 140 before the Common Era. And so that's over 2,000 years ago. Greek mathematician Hipparchus actually came up with 6 possible ratios, but decided 3 of them were the important ones, and then there are secondary trigonometric ratios, 3 of them as well. Whenever we take a ratio, it's going to result in a particular value. And if you're here in class, we're going to be discussing that in terms of this trigonometric table. But if you're not, let's go ahead and take a look at an example. So we're just trying to find trig ratios for this exercise. We're not trying to do any more than that, and we're going to express them as a decimal. And then we ask the question, are these angles for theta and alpha, are these 2 angles the same? So let's start, well, since I'm going to switch over to the colors that match, so let's start with theta. So I'm finding the trig ratios. So remember, you know what, I'll write it the way that so SOH CAH TOA, which is also SOH CAH TOA, SOH CAH TOA. Alright, so that tells me that sine, now remember, for this first one I want sine of theta. And I can go over here, particularly because I've got color here. So first of all, right angle is here, which means this 5, and I'm going to put that one in black, the 5 is always the hypotenuse. That is not going to change. For the red theta, this is the opposite angle, because that's across from it. And the 4 is the adjacent, I said opposite angle, I meant opposite side, and 4 is the adjacent side. So since sine is opposite over hypotenuse, well, what is opposite over hypotenuse? That's 3 divided by 5. And I said to express it as a decimal. This is going to be one of those cases where I'm actually telling you to go ahead and put it as a decimal, and that's equal to 0.6. Then cosine of theta, which is defined as adjacent over hypotenuse. Adjacent over hypotenuse, that would be 4 divided by 5. Pardon me, that's not right. 4 divided by 5, which is equal to 0.8. And the tangent of theta, which is equal to opposite over adjacent. And the opposite is 3, and the adjacent is 4, so that's equal to 0.75. Okay, so those are my 3 ratios. Now let's switch over to blue. This other symbol, just put it here, this is the Greek letter alpha, which is actually the first letter of the alphabet. That's the equivalent to the letter A. So this is the Greek letter alpha. And so let's do something similar here. The sine of alpha is equal to, now you don't always have to write opposite over hypotenuse, but I am going to label that here. Hypotenuse doesn't change. For the blue, this is opposite and this is adjacent. So it actually depends on which one we're looking at. So for alpha, the sine of alpha is opposite over hypotenuse, which is going to be 4 divided by 5. 4 divided by 5, which is equal to 0.8. The cosine of alpha is equal to, cosine is equal to adjacent over hypotenuse, but I need the blue ones now. Adjacent over hypotenuse, 3 over 5, and that's equal to 0.6. And then the tangent of alpha, which is, the definition of tangent is opposite over adjacent. So from alpha, from the blue angle here, opposite over adjacent, that's 4 over 3. And I really actually don't like writing this as a decimal. All of these other ones are non-repeating decimals. This one is approximately equal to 1.333. So that being the case, it then asks the question, are these angles the same angle? Well, if they were the same angle, then the sine of the angle, if the angles are the same, then the sine of the angles are not the same, or would be the same. But are they? They are not. The sine of theta is 0.6, the sine of alpha is 0.8. And that would be true for any of them. So you could use any of these to show that they're not the same angle. The cosine of theta is 0.8, the cosine of alpha is 0.6. These are not the same. So therefore, since, how do I say this? I want to be careful. I was about to say since no ratios are the same, but you might say, well, hold on a second. Sine of theta is the same as cos of alpha. And there's actually a connection there, but it's not one that we're going to make use of. So what I'm going to do is I'm going to say something like, since the sine of theta is not equal to the sine of alpha, therefore theta is not equal to alpha. And I could have done this for cos, I could have done this for tan. Okay, take a look at another example. Okay, that's interesting. Now I've been asked to solve for this. Now there's 2 ways you can do this, and I'm going to show you both. There's the way that I think a lot of students will be inclined to do this, which is cosine of 70. Well, you might actually wonder, what am I supposed to do with that? If you take a look at your calculator, you should have, if you have a scientific calculator, you have a cos button, COS. And depending, some calculators let you enter these things first or second, depending on the display. You're going to have to experiment with it. But I'm going to calculate the cosine of 70 degrees, and it turns out that that is equal to approximately 0.3420. And since I've done that as a decimal and it's rounded, I have to say approximately x over 15. And you can probably understand why I don't like this already. My first step is I've made this less precise. It's now approximate. Then I'm going to remember that this is still something over 1, so I can cross multiply here. And so I actually end up with x is approximately equal to 15 times 0.3420. And so x is approximately equal to 15 times 0.3420 and that is equal to 5.13. You can see because of the way this multiplied out, I've lost even more. I don't like that. I've lost even more precision here. This would be okay if you were rounding your answer maybe to 1 decimal place. My preferred way of doing this, so let me just shift all of this over a bit. So that's okay, but my preference here would be to do your cross multiplication first. So again, this is still true. This is still over 1. So now when I do my cross multiplication, I end up with x equals 15 cosine of 70 degrees. Traditionally, when we are multiplying something by a trigonometric ratio, we put the number we're multiplying by or the variable we're multiplying by in front, and then we put the ratio afterwards. And now, even though I'm still going to get an approximate answer, what I'd like to do is I'd like to do this whole thing in one step on my calculator if I can. So it's 15 multiplied by the cosine of 70. And I'm not going to get a hugely different answer, but what I am going to get is I'm going to have more decimal places available to me, and I can have as many as I like to write. So I'm going to write it to 4 decimal places. At least now I'm choosing to round it, as opposed to here, because I had to round this, I might have lost some precision. So both of these are correct. You can see the answers are quite close to each other, but I really prefer if you do it this way. Do your cross multiplication first. Don't change cosine or don't change your trigonometric ratio to a number until the very end. Okay, and let's see. Now, what about going the other way? What do I mean by going the other way? Here, I gave you the cosine of a number, and we had to solve for this variable over here. What if I were to give you a question where I actually ask you for in this case, the sine of a variable, and I tell you what that's equal to? So essentially what I want you to do is I want you to find what is theta equal to. If the sine of theta gives me this value, what does theta give me? And so you can see I've given you a little bit of help up here. If you go to your calculator and you punch in sine of 30, you'll end up with 0.5. If you take that answer, somewhere on your calculator you should also have a sign with a little -1 exponent. That's known as the inverse sign or sine inverse. And if you take the sine inverse of 0.5, it brings you right back to 30, which is what we started with. So what we're going to do now is take the sine inverse of 0.524. And if you put that in your calculator, again, we're going to have an approximate answer. So I'm going to take the inverse sine of 0.524, and I end up with 31.6009. And I might round that to 1 decimal place in the end. So theta is equal to 31.6. And actually something I forgot here, the angle's in degrees, the angle's in degrees. You need to put that unit in there. For this next one, same thing I said before. I don't want you to resort to your calculator until you've done as much algebra as you can. So what I'm going to do is if cosine theta equals this fraction, then theta is equal to the cosine inverse or the inverse cosine of this fraction. And now I try to do this all at once in my calculator if I can. A lot of calculators have brackets, so you can use those to put in the fraction all in one step. And that is equal to approximately 28.9550, which I might round. Theta is approximately equal to, well, if I round this up to 1 decimal place, it actually rounds to 29, and I don't want to forget degrees, because this 5 rounds this 9, but that rounds that 9 up to a 0 with a 1 here, so 29.0. You need, if you're not comfortable with this, you do need to get good at doing this on your calculator. And finally, we kind of go back to our original question, which was, hey, let's find these angles. Now, when you find angles like this, you actually don't have to calculate every trig ratio. You just have to calculate one. So let's remind the fact that here's the right angle, which means my hypotenuse is there, and my angle theta has an opposite side here and an adjacent side here. So I'm going to use the sine of theta. I could use any one. I'm going to use the sine. The sine of theta is equal to opposite over hypotenuse. That's equal to 3 over 5. But that means that theta is equal to the sine inverse of 3 over 5. And theta is approximately equal to, and now I take the inverse sine of 3 divided by 5, and I end up with 36.9 degrees. Now, if I want to find alpha now, technically, I could just use the fact that theta plus alpha plus 90 degrees must be equal to 180 degrees, the sum of the angles in the interior, which means that alpha is equal to 180 degrees minus 90 degrees minus theta. So alpha is approximately, and I'm just going to use the theta right off my calculator here. So I'm going to get 180 minus 90, which of course is 90, minus the answer to my last calculation, and I end up with 53.1 degrees, and that's approximate. But let's say I wanted to do it another way. Let's say I wanted to do it using trigonometric ratios. This time I think I'll use tangent. So I could also, or I could have said the tangent of alpha. Tangent of alpha, here is opposite to alpha, here is adjacent to alpha. The tangent, if you remember SOH CAH TOA, SOH CAH TOA, tangent is opposite over adjacent. So opposite here is 4, adjacent here is 3. That means that alpha is equal to the inverse tangent of 4 over 3. And so alpha is approximately equal to, and if the rules of mathematics work out properly, then I better get the exact same answer that I did using just simple arithmetic up here. So 4 divided by 3, I take the inverse tangent of that, and not surprisingly, I end up with approximately 53.1 degrees. And I could have used sine or cos or tangent of alpha to find that answer. I could have used sine or cos or tangent of theta to find this answer. And that's it. That's it for our right angle, introduction to right angle trigonometry for this lesson.